Good morning all. Myself Ramya, Associate Professor, Department of EC in Hindustan College of Engineering and Technology. Today I am going to discuss on bias compensation techniques from electronic circuits. In this lecture I am going to discuss about introduction to bias compensation and its types like diode compensation, thermistor compensation and sensistor compensation. First, bias compensation. It refers to the use of temperature-sensitive devices like diode, thermistor, or sensistor, which provide compensating voltage and current to maintain the stability of operating point. Why is it needed? Bias stabilization actually improves the stability of operating point through negative feedback only, but it reduces the gain of the amplifier. Since the gain of amplifier is a very important consideration, we are going for bias compensation technique which provides the excellent bias and thermal stabilization. Bias compensation techniques are diode compensation, thermistor compensation and sensistor compensation. Diode compensation is preferably used to compensate the instability due to base emitter voltage variation and the instability due to reverse saturation current variation. So now we are going to discuss about the diode compensation for instability due to base emitter voltage variation. This is the circuit for the instability compensation for instability due to base emitter voltage variation. Actually, the base emitter voltage varies with 2.5 millivolt per degree centigrade. So, when temperature varies, base emitter voltage varies, which results in the collector current variation also. Due to that, there will be the instability in operating point. So, to maintain the stability of operating point, we are introducing a diode in the emitter of a transistor, which is of same material as a transistor. So, since here silicon transistor is used, diode is also used with the same material as silicon. Since they are of same material, both have same temperature coefficient of resistance. That is, when base emitter voltage varies with temperature, similar variation happens in diode also. And the diode here is forward biased by the voltage VDD through the resistor RD. So, when you arrive at the expression, the IB is given by this expression, which is VBB plus VD minus VBE by RB plus 1 plus beta into RE. When temperature varies, base emitter voltage also varies. The similar variation happens in VD also. Since they are of opposite sign, they get cancelled with each other, and thus the variation of VBE with respect to temperature is cancelled and the base current remains constant. When the base current remains constant, obviously collector current will also be constant, so that the operating point is maintained and compensation is effectively achieved. Next, diode compensation for instability due to reverse saturation current variation. Here germanium transistor is used, so compensation is achieved by means of using a similar material diode which is of germanium, and here diode is connected in reverse bias. Right? So, the reverse saturation current flows in transistor is given by IC0 and flows in diode is I0. So, when the reverse saturation current happens here, the similar amount of reverse saturation current also happens here because of temperature. And if you solve it, you will get the overall current is given by base current plus reverse saturation current I0. And actually, IC will become beta into I. Since I is constant, IC will also be constant, because we know that collector current is given by beta I minus beta I naught plus beta IC naught. When temperature varies, IC naught varies. When IC naught varies, similar variation happens in diode also, that is I naught also varies in a similar manner. Since they are of opposite sign, they get cancelled with each other, and you will get the expression as IC is equal to beta I, and I is constant. IC will also remains constant, so the operating point will be maintained, thus achieving effective compensation. Next is thermistor compensation. In thermistor compensation, thermistor is used as a temperature sensitive element which has negative temperature coefficients, which means that the resistance decreases exponentially with increasing temperature. Dou RT by dou T is a temperature coefficient for thermistor. This is the circuit for thermistor compensation, where thermistor is kept in this position. When the temperature increases, the resistance decreases. So the voltage across this base emitter voltage also decreases. When VBE decreases, which results in the reduction of base current also. This decrease in base current tries to reduce the collector current, which actually compensates for the increase in collector current which has happened because of temperature variations. Thus, we will get the expression like this, and so that if this equation tells that if there is increase in IC0, there will be the corresponding decrease in IB, keeping IC as constant. Since IC is maintained constant, compensation is effectively achieved by thermistor compensation. Next is sensistor compensation, where sensistor is used as a temperature sensitive element which has positive temperature coefficient, which means that the resistance increases exponentially with increase in temperature. This is a circuit for sensistor compensation, where the sensistor is placed in this position of voltage divider bias. When temperature increases, this resistance also increases. When resistance increases, the current flowing through this resistance will decrease. Obviously, the current flowing through R2 will also decrease. When the current flowing through R2 decreases, the base emitter voltage also gets decreased. When the base emitter voltage decreases, the base current decreases, which actually reduces the collector current, which compensates the increase in collector current which has happened because of temperature. Thus, compensation is effectively achieved. Next, advantages of bias compensation. This bias compensation improves circuit stability and accuracy, and it minimizes the influence of temperature changes on circuit performance, and it enhances system reliability. So, we have seen various types of compensation and its advantages. So where is it used? Its applications are it is used in power amplifiers, biomedical devices and industrial control systems. Conclusion. Bias compensation techniques plays a crucial role in achieving accurate and stable performance in electronic circuits. And it may be through diode compensation, thermistor compensation or sensistor compensation. These techniques contribute to improved reliability, precision and versatility in various applications. So I hope the basic idea of bias compensation and its applications have been clarified well.